All right, let's look at the example from the previous lesson, and we are going to use the bell curve and the empirical rule in order to do this. I have drawn your normal distribution curve, your bell curve, and I have labeled each part where I have the mean in the center, the 1 standard deviation, 2 standard deviations above and below, and we are going to take the information that's given to us and we're going to answer this question. So when I am told that I have a normal distribution in parentheses 42 and 5, I know that this first number represents the mean of my data and the second number represents the standard deviation. So I can label my normal distribution curve at this time. I have the mean is 42, my standard deviation is 5, so above the mean I'm going to add 5 for each standard deviation, and below the mean I'm going to subtract 5. So this would be 37, minus 5 would be 32, minus 5 would be 27. Now, the question asks me, what percentage falls between 32 and 57? So we are looking from here to here. In order to do this, I must be able to label those percentages from my empirical rule. I know this is 34%, 34%. This is 13.5, 13.5. Okay, this is 2.35 and 2.35. And to determine what percentage is from 32 to 57, I would just add those percentages together. So I would have 13.5. I have 2 of those, plus 2 34s. And I have a plus 2.35. And when I add those together, I get 97.35%. So the answer would be answer D. All right, we are going to be introducing a formula that allows us to find the probability of and z-scores of a set of data. We know that z indicates the number of standard deviations. So if it is 1 standard deviation above, then that means that we are looking at a z-score of 1. If it is 2 standard deviations below, then that means our z-score would be -2. So the z-score is the same as the number of standard deviations above or below. We are given a formula, z is equal to x minus the mean over the standard deviation. And what we're going to do is we are going to plug in these values. And I'll plug in x is 7.3 minus the mean, which is 3.1. That is divided by the standard deviation, which is 2.5. So I'm going to do that computation. I'm going to get 4.2 divided by 2.5. And I get a value of 1.68. Therefore, my z-score for this set of data would be 1.68. This tells me the number of standard deviations above that mean. All right, in class and on the SOL test, you are going to be able to have a table that is called the standard normal probabilities. This is in your content in terms of this week's lesson. It would be a good idea for you to print out that z-score table. This z-score table shows the probabilities or the percentages below that certain range. So if you have a z-score of 2, this table is going to give me the probability or the percentage about the information below 2. Right, to find the probability of the amount of data that is less than 1.36, all I'm going to do is go to that z-score table. And when I read from my z-score table 1.36, I find that I have a decimal of 0.9131. So the probability of getting a score, a number that is less than the z-score 1.36, would be decimal 9131. If I wanted to change this to the percentage of this data, what I'm going to do is move that decimal 2 places to the right, and I would have 91.31%, which means that 91.31% is below that certain z-score. Right, on our second example, we want to find the probability of a z greater than negative 2.62. So I'm going to do the same thing. I'm going to find negative 2.62 on my table. And on my table, that gives me the decimal 0.0044. Okay, what I'm going to do at this point is I am going to remember, oops, this table only gives me below. So because this is above, I have to subtract this decimal from 100% or from 1. And when I do that and I subtract from 1, I'm going to get 6599 decimal. So my answer is going to be, the percentage is, the probability is 0.9956. If I was to change that to the percentage, it would be 99.56%. The last example is between. And when it is between, you are going to have to find the decimal for each of these parts. So my first part, I have z is less than 0.54. Okay, because that is less than, I'm going to go to my table, and I have 0.54, and I read the decimal 0.7054. And let me double check and make sure that that was the correct decimal. Yes, 0.7054. Okay, I have negative 2.9, and I'm going to read from my table negative 2.9, and when I do that, negative 2.19, I find that I have a decimal of 0.143. To find between those two, I am going to then subtract the largest minus the smallest. And when I subtract, I'm going to get decimal 6911. So the probability that the number that I'm looking at is going to fall between those two z-scores is 0.6911. If I change that to a percent, that would be 69.11%. All right, on this one, we're given the information for the mean, the standard deviation, and we're given a value for x, and we are finding z. We are going to be using that formula. Z is equal to x minus the mean over the standard deviation. I would have z is equal to x, which is 12.1, minus the mean, 5.8, divided by 3.6. All right, completing that computation, I would have 6.3 divided by 3.6, and when I do that, I get 1.75. So that tells me that this element x, which is 12.1, is 1.75 standard deviations above that mean. Right, in this one I am using the z-score formula, but I am not finding z. I am actually finding the value of the mean. I have gone ahead and replaced z with its value, negative 1.24. X is 15.44. We're finding the mean, so it's going to be minus mu divided by 1.5. The first thing that I'm going to do to solve this equation is to multiply both sides by 1.5. And when I do that, I get as an answer negative 1.86 is equal to 15.44 minus the mean. To solve this, I'm going to get rid of minus 15.44, subtracting that from both sides. And when I do that, on the right side, I'm going to get negative mu. On the left side, I'm going to combine these together. And I get negative 17.30. Because this is a negative mu, I am going to be dividing both sides by negative 1. And I find that my answer is 17.30 is equal to the mean, which was answer A. All right, in this problem, we are told that Claire scored 720 on the math portion of the SAT. Nick scored 31 on the math portion of the ACT. The average math score on the SAT was 515 with a standard deviation of 116. The average math score on the ACT was 21 with a standard deviation of 5.3. Who performed better? That is basically asking who has the highest z-score. So I'm going to list the information that I know. I know Claire scored 720, so that means x equals 720. On the SAT, the average was 515, so that means the mean is 515, and the standard deviation was 116. So I can go ahead and compute what Claire's z-score is. So I'm going to have z is equal to x minus the mean over the standard deviation. Z is equal to 720 minus 515 divided by 116. I'm going to simplify, and when I do that, I get 205 divided by 116. When I do this computation, I get z is equal to 1.76724,138. And we know that from the previous material that your z-score is always going to be in terms of hundredths. Therefore, this 7 after the 6 tells me to round up to 1.77. Now, I'm going to do exactly the same thing for Nick. I'm going to take this information. I know Nick scored 31. I know the mean on the AC test was 21. And I know the standard deviation was 5.3. So I am now going to plug that into my z-score formula. And I'm going to get z is equal to x minus the mean divided by 5.3. That's going to be 10 divided by 5.3. And when I do that computation, I get z is equal to 1.88679245. When I round that to the nearest hundred, the 6 tells me that I'm going to round up to 1.89. Now, the question asks, who had performed better on the test? Who had the highest z-score? That was Nick. Nick's z-score was higher, therefore he performed better. All right, on the first example, we are finding the probability of a z-score less than 1.78. Less than, remember, does mean below, and below is what our table shows. So I'm going to go to my table, and I'm going to look up 1.78, and I see that it is the decimal 0.9625, which is answer A. Okay, second example, we're finding the probability of a z-score greater than 2.46. Remember, the table shows below. Greater than indicates that we are looking for the amount of data above that particular z-score. To get that, we have to subtract the decimal from our table from 1. So when I look up on my table 2.46, I get 0.9931. Notice that's an answer, and that's how an SOL test will try to trick you. They'll actually give you the correct answer for the information below. When I subtract, I get 9600. Therefore, my answer is decimal 0069. All right, on this example, we are finding the probability of the z-score between negative 1.21 and 2.06. To find this information, I'm going to read from my table, negative 1.21, and that is going to be decimal 1131. I'm going to read from the table 2.06, and when I do that, I get 0.9803. And to get my answer, I'm going to subtract. So when I subtract those, I'm always going to have the largest minus the smallest. And when I subtract, I'm going to get decimal 8672, which is answer D. All right, on this example, a normally distributed data set of 600 values has a mean of 32, standard deviation of 8, and we want to know how many values will be above 46. So the first thing that I'm going to do is I'm going to find my z-score. And to do that, I'm going to plug into my formula. And I have 46 minus the mean, 32, divided by the standard deviation, which is 8. That's going to give me 14 divided by 8. And when I divide that, I get 1.75. So I'm going to go to my table and I'm going to look up 1.75. And when I do that, I find 0.9599. Right, so from my table, a z-score of 1.75 is 0.9599. Now, it asks me, how many values will be above 46? Remember, when it is above, that we have to take that decimal and we have to subtract it from 1. So I'm going to subtract 0.9599. 9 from 10 is 1. And I get decimal 0401. It asks me how many values. When it asks me for how many, that means that I need to take the decimal that I got from my z-score table, and I need to multiply it times the total number of data set, which is 600 values. And when I multiply I get 24.06. So when we are finding how many a certain number, anything that is after the decimal point is automatically dropped, which means that my answer is going to be 24. So that one is a pretty detailed problem. You have to find the z-score first. Because it is above, we have to subtract that decimal from 1. Then we have to multiply that decimal times the total data set, which is 600. All right, in our problem, we have a sample of 2,500 men was found to have a normal distribution with their height. The average height is 71 inches with a standard deviation of 1.5 inches. Approximately how many men had an average height below 69 inches? So that word below tells me that I can read directly from that table. So I'm going to find my z-score. I have z is equal to x minus the mean over the standard deviation. Z is going to be 69 minus 71 over the standard deviation of 1.5. When I simplify this, I get negative 2 divided by 1.5. And that gives me negative 1.333 repeating. Remember that your z-score has to be hundredths, so that is going to be negative 1.33. So I'm going to go to my z-score table. And from my z-score table, I'm going to look up z equal negative 1.33. And when I do that, and as you can hear, I am looking at my table, negative 1.33 is 0.0918. To get how many men are below, okay, we are going to do how many. Then I'm going to take that decimal, 0.0918 times 2,500, and I get 229.5. We cannot have a half of a person. We are going to drop that. So my answer is 229 men would have an average height of below 69 inches.